Hi viewers. Welcome to this presentation on power system frequency. This is a sketch of regulating tank in water distribution system. Functional detail is discussed in previous video on active power matching mechanism. There is one inflow line IA is from very large water source having steady water level. One outflow line OA is from bottom of the tank going to water users. The water level in tank is steady till inflow and outflow are equals. The water level in the tank drops due to net water shortage when outflow increased due to user requirement. Input water head high from water level in the tank to water level of reservoir increases due to drop of water level in tank. Consequently, inflow increasing automatically. Similarly, the water head ho from outlet at bottom of tank to the water level in the tank decreasing with drop of water level in the tank. Consequently, outflow decreasing automatically. This phenomenon of increasing inflow and decreasing outflow continues till increased inflow matches with decreased outflow. Thereafter, water level in tank is again steady at little lower level. More details available in video Active Power Matching Mechanism. Power system also operating the same way. Generator is injecting active power in the system. User's load is drawing active power from the system. The frequency is steady till power injection and draw is equal. Power draw increases when consumers start more load. The system frequency starts dropping due to shortage of power. Governor system is increasing input to power plant with speed drop. So power injection is increasing automatically. Similarly, load demand is decreasing with dropping frequency on account of frequency sensitive loads. Both these correction continues till power injection and draw is balanced. Frequency is again steady at slight lower level. This is a chart of active power versus frequency for power system. Initially, system is operating at O with generation go, demand do and frequency fo. Now demand increased from do to dx. Dx is higher than do, means there is power shortage in the system. Therefore, frequency drops from Fo to Fn. Generation increased from Go to Gn as per governor control. Power demand decreased from Dx to Dn. Operating point has shifted from O to N when demand Dn is equal to generation Gn at frequency Fn. This was for basic power system with single power plant and single load center. Actual power system have more power plants and many load centers. So here is modified regulating tank setup as shown with two inflow lines IA and IB and two outflow lines OA and OB. Water level in the tank remains steady till total inflow from both the lines is equal to total outflow to both the lines. Now, as earlier case, the water requirement increased in supply area of OA. So outflow from OA increased. Now total outflow is more than total inflow. So water level starts dropping. Consequently, input head high is increasing with dropping water level in the tank. Hence, inflow through valve IA is increasing automatically. Input head high is common for both inflow lines. So inflow through valve IB is also increasing automatically. Outflow head ho is decreasing with dropping level. This head ho is also common for both the outflow lines. Hence outflow from both the lines OA and OB is decreasing. This will continue till total inflow matches total outflow. Thereafter water level in tank is steady. In this setup the mismatch of flows occurred due to increase of outflow from OA is automatically adjusted due to increasing inflow of two lines and decreasing outflow of two lines. Therefore flow matching is quick with less level drop. In case of more inflows and more outflows the level drop may be still smaller. Larger power system with more power plants and numbers of load centers have similar effect. Frequency drops due to load rise in any center. All the power plants are operating in synchronism and frequency is common. So generation raised at all power plants by governor system. Same way load demand drops at all load centers and frequency drop is smaller. Therefore power systems are operated in interconnected grid mode for better stability. Here is single line diagram of three power systems: orange A, brown B and green C. The magenta box represents power plant with generation. Cyan box represents load centers with load. Blue lines is the network connecting power plants and load centers in the system. Bold box of matching color indicates frequency of respective power system. Initially there is no interconnections between these power systems. Power systems operating in independent mode. So variations in load or generation in any system affects the frequency of respective system only. So frequency of all the three systems are monitored during following exercise of variation of load and or generation in any system. Start with power system A. Reduction of generation at any power plant in system cause frequency drop. Frequency improves when picking generation at any other power plant in the same system. Similarly, rise of load at any load center causes drop in frequency. Picking some generation at any power plant improves frequency. Load shed at any center further improves frequency. During this exercise, frequency changes observed in system A only, whereas frequency of system B and C have no change. Similarly, variations of load and or generation in system B or C have local effect without affecting frequency of other systems. Now all the three systems are interconnected. Red lines are interconnecting tie lines. Red bold box indicates grid frequency, which is common for all three power systems. Now individual system frequency is meaningless. However, its display continued for comparison of isolated system frequency with grid frequency to observe the difference with grid system. First, observing the effect on frequency due to variations of load and or generation within one of the power systems. Frequency drops when generation reduces at any power plant in the any system. Mark that drops of grid frequency is smaller compared to drop of concerned system frequency. Now observing the effect for variations of load and or generation anywhere in the grid. When generation reduces at any power plant in any system, the grid frequency and concerned system frequency drops. Grid frequency improves when generation picked at any power plant in other system. But concerned system frequency rise above normal whereas other system frequency continue as it is. Grid frequency responds to all rise drop of load generation at any power plant or load center in any system. Whereas isolated system frequency is confined to changes within the system. So there may be condition that individual system frequency is abnormal high or low but grid frequency is well within operating range and operates smoothly. Individual system abnormal frequency is ineffective and no adverse impact. Grid mode operation is preferred due to various advantages. Grid mode operation is more stable because of larger system bias and higher inertia. Frequency excursion is smaller and slower. This allows time for corrective action and its effect to avoid cascading and blackout. Also, power reliability is better in grid mode due to numbers of power source and multiple network links. Other advantage is about peak load management. Day-night cycles in western area lags behind the eastern area. So spare power of one area during off-peak is useful for peak requirement of other area. Northern area is cooler than southern area. Heating load in winter is predominant toward northern area whereas cooling load during summer is predominant toward southern area. Similarly, different areas have different local holidays. Spare power of one area due to holiday is useful to other area. The diversities in power requirement in different areas helps in better management peak power. Equitable distribution management. Casual variations in power requirement in any area may be due to drought, cyclone, earthquake, flood, agitation, strike, tripping of major load area, etc. Power availability in any area is severely affected due to various reasons like multiple forced outages of power plants, like boiler tube leakage, auxiliary failure, fuel supply link disruption, loss of power outlets, workers strike, etc. So there may be situation when some area is comfortable or surplus in power while same time other area is facing shortage or starving of power. It is very feasible to manage equitable power supply throughout just by sparing a part of power by all others without much difficulty. Optimizing input power cost. Cost of power produced depends on many factors. Types of raw energy input like coal, oil, gas, naphtha, hydro, nuclear, etc. Cost of transport vary with the distance of source and power plant. Efficiency of plant also play role in cost of generation. Cost of power may be different at various power plants. Linked system facilitate to inject cheapest power on priority following other power according to cost factor. However, there are few drawbacks in grid mode operation. Fault level increase at some strategic locations due to multiple power sources and strong network in the grid. It requires review and upgradation where necessary. Power flow in network depends on quantum of power injected at various sources and power drawn at various locations. There is no direct control on flow of power in any section of network. Sometimes this causes tripping of critically loaded link. Few cases it may initiate cascading and partial or widespread blackout. However, it may be possible indirectly by restricting power push by restricting injection from upstream of sending end of critical loaded element. Other way is restricting power draw in downstream of receiving end of critical loaded element. Alternate rude, cruel method is equally risky and not recommended or very rarely resort to in extreme emergency. It is diverting power flow through other route is to increase impedance by switching off feeding in line to critical element or exporting out line from critical element. Such indirect operations are very difficult and delayed, particularly when switching operations required is in the system other than affected system. Long-term solution for similar critical links is to provide parallel lines using phase shifting transformer or HVDC link. Grid system have many participants for generation, transmission, distribution, bulk users and controls. All are operating for their benefit as per own policy and targets. Any participant not adhering to operating discipline and control instructions or delay may lead to unhealthy operating conditions like critical loading on any line or transformer, abnormally high or low frequency. Abnormal frequency is unfavorable for certain application and in particular detrimental to rotating machines, causing excessive vibration and mechanical damage. Also, any incidence of faulty maloperation anywhere in the grid may have widespread effect in grid operating as single power system. So operational control is difficult. But vigilant monitoring and timely directives by ALDC, SLDC, RLDC and NLDC makes task manageable. With all these pros and cons, grid mode operation is preferred with due safeguard measures. Please like, subscribe and recommend others if found worthy. Viewers' comments welcome. Thank you, viewers. Bye until meet again in next episode.